This conference will now be recorded.
Okay, again, so I wanted to appreciate everyone for taking the time today. My name is Matt Sorensen. I'm the technical specialist with KOSTER American. Today's presentation is going to cover our curtain wall injection products as part of our negative side waterproofing systems. The first question that's always asked in terms of waterproofing below grade structures is obviously what's the best method? The best method is always normally to waterproof from the positive side, which means the side which is directly exposed to the water source. This diagram here shows the difference between the positive side of a structure and the negative side. Primary reason that waterproofing from the positive side is most effective is the ability to visually see the insulation and ensure that the wall has been waterproofed correctly before backfill is installed. Most positive side waterproofing coatings can afford to be a little more elastic and flexible to bridge any cracks which form, where most negative side waterproofing coatings are usually more rigid, high compressive strength. So positive side coatings can be installed with a little bit of flexibility in the case of potential movement of the building or so on, potentially causing cracks in the structure. However, waterproofing from the positive side on existing structures or the outside of an existing structure is very rarely a feasible option for several reasons. Primarily, we get the substantial costs associated with excavating around any kind of below grade structure to expose the exterior. On the same card, it's often impossible to get to any areas in concern because of neighboring buildings, roads, or other obstacles which may come up in the vicinity of the building. Finally, the effect on any of the surrounding areas must be taken into account. For example, the closing of roads and any kind of effect this will have on the local community and the local area around the project. The goal of any project is obviously to perform the work for as low cost as possible and as short of a time as possible, with as little disturbance to the surrounding area and community as possible. Most of the time, all of these factors prevent waterproofing from being installed on the exterior of existing below grade structures because of the lack of feasibility to expose the outside of a below grade structure. So what do we do in that case? We have systems to install as part of negative side coating systems, but primarily what we install in these kinds of scenarios, we install negative side waterproofing systems by curtain injection, by blindside injection through the wall. This is where negative side waterproofing will come into play. These systems are installed from the inside of a below grade structure, eliminating the need to expose the exterior. One of the most well-proven methods of waterproofing from the negative side is by injection, also called blindside injection. This is most commonly performed by curtain wall injection, but it can be achieved by area injection into the structure or by injecting waterproofing material into leaking joints. A common misconception of negative side waterproofing is the thought that one installation in one leaking area will stop the problem permanently. Injection materials, especially blindside curtain wall grouting materials, don't simply make the water disappear. They provide a waterproof seal in that specific area where they're installed. As we all know, water follows the path of least resistance. So if injection is used in distressed or leaking areas, it's very possible the water will move and cause distress in other areas. When using these products solely in isolated areas, it's important to manage the customer's expectations, meaning that several installations may be necessary over isolated areas to monitor the movement of water and to ensure a completely waterproof structure. Blindside injection, like we discussed, is normally used as part of a system with other negative side waterproofing approaches, including crack injection and cementitious negative side waterproofing coatings as part of what we would call a belt and suspender systems approach to completely seal the area. Curtain wall grouting is the most commonly used method of blindside injection and negative side injection waterproofing. It's a process where injection material is installed into the ground on the outside of a structure. The grout is pressure injected directly into the soil through ports which are installed through the entire thickness of the wall. The ports are closely spaced to ensure that material flowing from each port overlaps with the next, creating a continuous curtain along the outside of the structure. As shown in the graphic, material injected through each port forms a grout ball, which should overlap with the balls of material injected through adjacent ports. Oftentimes, ports are left open during injection to ensure travel of material along the outside of the wall. These curtains are elastic to ensure coverage in case of future cracking in the structure and are highly chemical resistant. Area injection is usually performed on more porous substrates like brick or some kinds of masonry. Holes are drilled at very close proximity to each other to a depth of about half to 90% of the thickness of the wall. A low viscosity injection material is pressure injected into the ports. The low viscosity of the grout allows it to travel through the pores and the capillaries of the masonry, as well as through the mortar joints. This creates an internal waterproofing barrier within the wall itself. Finally, the third common application for negative side injection is for void and joint filling. This is most commonly performed in leaking expansion joints, both vertical joints and horizontal joints. When you're injecting into a joint, one of two methods are used. The most common method is to perform the work like a normal crack injection, drilling ports on alternating sides of the joint. Material is normally injected behind the existing water stop or waterproofing if there is one present. The other method is to use surface-mounted injection ports, which do not require drilling into the substrate. When injecting overhead vertical joints or horizontal joints, obviously some kind of surface seal or surface sealing material must be installed to retain the material. Obviously in an overhead joint or in a vertical joint, we don't want that material flowing out of the joint. We want it to be kept in the wall. So we need to have some kind of surface seal present there to retain the material in the void. Void filling is performed similarly with grout used just to fill void spaces and create a waterproof barrier. This is most common at interstitial spaces between inner and outer walls, around tunnel walls, and other applications where interstitial spaces may be present. These are sometimes filled with foam products as well, but void filling with foam is not as long-lasting of an approach in a system. Foams do tend to break down much more quickly than, well, they break down over time either way over a relatively short lifespan compared to these injection grouts and these injection materials that are designed to have much longer lifespans and aren't affected as much as any of the polyurethane foams may be. Injection grouting materials of the past included clay, cement, and bentonites, which were not particularly chemical resistant as some products which are manufactured today. Cementitious products are by nature obviously very, very rigid and are susceptible to cracking over time, which could allow further breaches of the system. Altogether, these products created the need for flexible, polymer-based systems which are highly functional and much more long-lasting. Polymer grouts, which are flexible, elastic, and highly chemical resistant, are the ideal products to use for a negative side current injection. The systems that KOSTER provides that we're going to focus on are polyurethane gels and acrylate gels. A gel is a state of matter between a liquid and a solid, and these gels provide excellent retraction, elasticity, and flexibility among multiple other important physical properties. Polyurethane gels have been the workhorse in terms of void injection and curtain injection for a very long time and for good reason. They're highly chemical resistant and very elastic systems which provide ideal physical characteristics for a long-term successful installation. Polyurethane gels are typically one component mixed with water during injection. They're usually installed through a two-component pump with a variable mixing ratio, which allows the material to be mixed with water at ratios from 1:1 all the way to 1 to 13 parts gel to parts water. So that would be 1 part gel up to 13 parts water. Changes in the amount of water mixed in the ratio will change the viscosity, reaction time, and penetration range of the mixed material. The mixing ratio can also be adjusted case by case depending on the amount of water present behind the wall, as the gel will use water present behind the wall as part of the reaction after injection. Viscosity of the material ranges between 600 and 800 centipoise depending on temperature, which is similar to castor oil or glycerin. When injected, depending on the mixing ratio, the viscosity can be as low as 20 centipoise. So that would be at 1 part water, or excuse me, 1 part gel to 13 parts water, we'd get a viscosity of close to 20 CPS. Water has a viscosity of about 1 centipoise. So it is fairly low viscosity relative to other products. Time of reaction, depending on the mixing ratio, is between 1.5 minutes and 3 minutes. Since it's mixed with water, application temperature must be above freezing. When installing at temperatures below 50 Fahrenheit or 10 Celsius, it's important to take into account the effect the temperature will have not only on the viscosity of the material as being injected, but also on the reaction time. Very low temperatures will affect reaction time. Materials will take longer to react at lower temperatures. Since these products react with water, any tools, equipment, or machinery must be cleaned with a suitable solvent or cleaner after injection, and pumps should be stored in a way to ensure that no material can react inside the pump, mixer, or any injection component. KOSTER's polyurethane injection product is the KOSTER Pure Gel, normally installed with the Pure component KOSTER Gel Pump. The KOSTER Gel Pump is ideal for injecting this product. It's easily adjustable to change the mixing ratio of water to gel, allowing for quick changes to the injected material's physical characteristics based on field conditions and installation conditions. So if it's noticed that there is a large amount of water behind the wall and you want to turn that ratio down to encourage the material to mix and react with the water present behind the wall, it's very simple to make those changes on the job site with very little downtime. Acrylate gels are fairly new in the world of curtain injection, but are great products which have excellent tear resistance and elongation properties among other properties that make them highly functional and well suited for these installations. These products are typically 3 components: a methacrylate mixed with an acrylamide to form the A component, and a sodium or ammonium sulfate mixed with water to form the catalyst, or the B component. In the case of joint injection, the water is usually replaced with the polymer dispersion because the dispersion greatly increases the tear resistance and bond strength of the material. Viscosity of the material when injected is about 4 centipoise, and when the polymer emulsion that we'll discuss later is used in joint injection primarily, the viscosity changes to about 30 centipoise. The low viscosity allows for much longer travel of material and excellent penetration into tighter voids. These products are mixed 1-to-1 ratio of A to B, but the ratio of salt or acrylamide can be adjusted to create a variable reaction speed. Reaction times can vary from about 20 seconds to 15 minutes depending on the product used and the ratio of components added. The shorter reaction times are obviously ideal for active leaks and for preventing excessive runoff materials in looser substrates or soils. Longer reaction time allows for deep penetration before reaction, giving the material a chance to spread through the matrix behind the wall and form the curtain which is desired. Again, minimum allowable temperature is freezing for installation of these products. Neither A or B component will react with plain water, so water can be used to clean the pump and any equipment, making for a much easier cleanup process at the end of the injection phase. KOSTER G4 is the all-purpose acrylate injection gel with a very low viscosity and 15-minute reaction time, which allows for significant penetration into substrates and soils. The A component is combined with the A2 component, and the B is added with 5 gallons of water, so the material is injected at that 1-to-1 ratio by volume. KOSTER S4 is a product designed with an adjustable reaction time from 20 seconds to about 3 minutes, which allows for faster reaction in conditions where active leaks may be present. The same installation procedure can be followed, but KOSTER S4 can also be used with the B+ additive, that polymer emulsion that we discussed, which increases elasticity, retraction, and bond strength, as well as elongation. B+ additive replaces either some of the mixing water or all 5 gallons of the mixing water in the reaction. Again, different amounts of the B+ that are added will affect reaction time of the mixed product. This is most commonly used in joint sealing applications. KOSTER Acrylate Gel Pump is a pneumatic pump specifically designed for use with these products. It pumps both A and B components at a 1-to-1 ratio. Material is pumped separately and only mixes at the distribution nozzle. There's also an internal flush, which can be used port to port to clean the mixing head. Oh, sorry. There we go. Can be used. So the pump has an internal flush, which can be used port to port to clean the mixing head and nozzle to ensure that mixed material does not react, or there's no reaction of material in the mixing head. Since neither component will react with plain water, the pump can be flushed and cleaned with water, so there's no need for any harsh chemicals or solvents to clean these pumps. Injection ports are drilled in a diamond pattern with a standard spacing of about 10 to 12 inches. An injection is performed from bottom to top, moving upwards and following the grid pattern. A rule of thumb is approximately 40 strokes of the pump per port, done in several different stages. That 40 strokes of the pump ends up being about a half a gallon of material per port. Again, this is all, as a rule of thumb, different job conditions and different installation conditions will obviously make that vary, but that's generally a rule of thumb, a good place to start. Material is injected in overlapping phases to ensure full coverage of the curtain along the backside of the wall. Working from bottom to top creates what we call the shingle effect, where grout is installed on top of other grouted areas, overlapping from the top, filling voids as it settles and reacts. So we get a settling of the material as it's injected over material that's already reacted, and it fills any voids that it comes into contact with, or fills and reacts, creating that shingle effect and giving us a seamless installation. So we have an example here of standard installation. Obviously, as a graphic, we would, during normal installation phase, we'd start at the bottom, but we've got our grout ball, and what we're doing is we're injecting phase by phase to ensure that we're getting that overlapping and the curtain of material along the back side of the wall. As an example, here's a mock-up that we did. This is one of our standard kind of training demos where we will create a wall and just backfill with normal soil, inject through the wall to show the performance of the materials. The center picture there is the KOSTER G4 that we injected through the standard injection ports at 12-inch spacing into that substrate. The picture on the right is the KOSTER S4, which has that shorter reaction time. So you can see, instead of maybe penetrating all the way back through the wall, it reacted much more quickly and formed its barrier a little bit closer to the back wall, the back side of the substrate. Again, so what we're looking for here is we have some more pictures later on of what we've discussed, those grout balls, those circular shapes which can be formed by the injection material as it's injected. In the real world, though, this injection material, especially since it is low viscosity, it's going to behave as water will and will follow any kind of path of least resistance, filling voids along the way. So we don't always get those obviously ideal, perfect grout balls. But as you can see here, we've pulled the plexiglass back. We have a solid wall where the material has consolidated any voids and reacted and given us that barrier that we're looking for of that waterproofing material. So this brings us to our big question. On any particular project, which is the material to use? Both types of products have adjustable mixing ratios, which allow the user to shorten or extend the curing time of the material depending on project conditions. Both can be used in active leaking situations, and they both use water present in the injection area as part of their reaction and curing. And especially the acrylate products, the G4 and the S4, if they encounter water behind the wall as they're reacting, that can we use water outside of that 1-to-1 ratio potentially, and it can swell with exposure to water after curing. So it can also, after it's cured, if it's exposed to water on the backside, it can swell and expand, giving an even better waterproofing barrier, creating that barrier, even ideally after the product is finished curing. Acrylates are generally better at penetrating through water immediately after injection, based on a chemical compound which allows the material to cut through water, preventing it from being washed away as easily in a situation with moving water behind the wall or an active leak. The higher viscosity of the polyurethanes means less penetration generally into substrate voids and soils. This means polyurethanes are generally less effective in soil stabilization, but also means the material often cures in place without the risk of the gel traveling too far before the reaction begins. With their low viscosity, acrylates penetrate better into soils during injection and allow for more travel in both horizontal and vertical applications. The adjustable reaction times of these products, down to as little as 20 seconds, allows them to be injected to cure in place as well as traveling and penetrating. So with the acrylate products, we can inject the cure in place in about 20 seconds, or we can inject with a more of the 15-minute reaction time, allowing us to travel and penetrate a little bit farther, in using the same kinds of products for both purposes. The main difference between the cured products is the requirement of a moisture source for acrylate products. If left to dry completely, these products may become rigid and shrink slightly, increasing the potential for an effect on the performance of the cured product. Now, this isn't something that just happens overnight or instantly. Normally, a completely dry period of greater than 3 months is required to cause material to dry out and shrink. When these products are re-exposed to water, acrylates will return to their original form and their original shape and become more gel-like instead of remaining as rigid as they are when they completely dry out. All the material needs is ground moisture to remain elastic and flexible. Polyurethane gels will be less affected by dry periods and they will not reswell or return to their original form if exposed to moisture after any potential shrinkage has occurred. Finally, acrylate products have far better physical performance in terms of tear resistance, elongation, bond strength, and elasticity. For a long time, polyurethanes were the top dog of curtain wall grouting because of their impermeability and resistance to chemical exposure in alkaline or acidic environments. These products won't break down over time, and they offer the potential while injecting to alter the mixing ratio to speed up the setting time in situations where lots of flowing water is present. Since their introduction, acrylates are obviously also very commonly used in circumstances where tight soils and low viscosity is required to penetrate into any tight soils without voids, and for the curtain of grout that is desired. By changing the mixing ratio of the three components, the reaction time of the product can be altered down to 20 seconds to stop active leaks or to prevent runoff of the material in loose soils. When using acrylates, again, care must be taken to ensure that the material will not be allowed to permanently dry out and will have some source of moisture. The picture on the bottom left is a polyurethane injection that we did just a sample mock-up with the pure gel, and you can see how that material, based on the viscosity, doesn't really penetrate and fall like water will, but we get those grout balls and we get the formation along the backside of the wall, which is exactly what we're looking for. For area injection, acrylates are always chosen over polyurethane products. Low viscosity of the material allows the acrylate to penetrate into the finest pores, voids, capillaries in the masonry and in mortar joints, which flows and creates a barrier. Towards the bottom of the picture here, you can see the acrylate material running out of the sides of the prop with the injection port about 1.5 feet away. So you can see that material is so low viscosity, and when it's pressure injected, you can see how it flows through every single capillary and void and creates that barrier within the substrate. In the application of joint injection, both products offer viable options. Polyurethane gels offer good elongation and good bond strength to flanks of joints, but performance of acrylates in terms of elongation, bond strength, and tear resistance are much, much higher. Pictures along the bottom in the middle of the slide are of the KOSTER S4 used with the B+ polymer emulsion dispersion to increase the elongation and bond strength of material. As a case study, we're going to discuss the question. As a case study, we're going to discuss the project we worked on, the West and South Foundation walls at the Empire State Building in New York. In 2014, we provided materials for a waterproofing project in the basement of the Empire State Building, specifically curtain injection of the West and South Foundation walls of the basement. The owners wanted to use these areas as office space, and they'd never been used or occupied in their existence. Based on drawings and scans of the walls, it was determined that the foundation walls, which were constructed in 1893, were constructed of brick, an average of 36 whites thick, so that's about 12 feet thick, with some concrete footings. Because the building was constructed on bedrock, the thickness of the walls varied greatly over their length. Additionally, the elevation changes in the bedrock made it difficult to determine a good place to inject material behind the wall. Finally, with so thick of a wall, it would have been very hard to deposit material on the outside, never mind the fact that active water along the backside of the wall, which is part of many of the island of Manhattan's underground rivers, would have made it very difficult to ensure that material was forming this monolithic curtain along the backside of the wall. Normally, the method of ensuring travel of materials is to leave adjacent ports open during injection. When material is seen coming out of an adjacent port, it means that material has made it as far as that next or adjacent port. In this scenario, obviously what we're dealing with in this project, it would have been impossible to expect material to be pushed back through the wall out of an open injection port. Shown in the picture on the right, an interstitial space between the courses of brick in the wall was identified about 2 feet from the inside of the building. It was decided that injection material would be deposited in this interstitial space. So, we can see by the way this project moves, the project was initially planned to be a curtain injection project, but this transformed into a void injection product. We were filling an interstitial space with injection material. This is where some of the ingenuity comes in, and we were able to provide a solution to the issues which were being faced by the customer. KOSTER Pure Gel was injected into this interstitial space over the course of several weeks. The material was installed using injection lances, as seen in the picture on the left. The entire waterproofing system of these areas utilize many products prevalent in negative side waterproofing, again, including waterproof repair mortars, polyurethane crack injection foams, and crystalline negative side waterproofing to create an entire systems approach, a waterproofing system from curtain wall and injection waterproofing all the way to a negative side capillary crystalline coating. Obviously, several years later, these spaces are occupied and they remain waterproof to this day. For additional information, we do have on our website some more case studies, reference projects, as well as technical information and specifications on the use of these products. Also, there's a contact tab there to reach out with any inquiries or for any more information regarding these products or any of our products. Also on our website, under the products tab down below, there is a page which has the schedule for all of our future webinars and all of the training seminars we will be holding back in Virginia Beach eventually, and all of the webinars we'll be holding over the next couple weeks online here. I want to thank everyone for taking the time today to, again, be here for our presentation. I'm going to open up the floor now. If you do have any questions, feel free to submit those and I'll answer them. If not, or if you think of something later, I can be reached by email or phone. On our website, under that contact tab again, my name is Matt Sorensen, and I can be reached by phone or email there with any additional questions or for additional information. We will have a recording of this webinar posted to our website and to our YouTube, like I said, for future reference or to for any additional information. So thanks again for everyone taking the time to be with us today. I will open it up for any questions. Feel free to send those through now.